My name is Tselikis. I'm an application engineer at Altair, and I would like to present you how Altair help companies to overcome challenges with multi-physics simulations through our tool, Altair SimLab. So if you ever faced multi-physics analysis, I think here are some familiar questions like how we can reduce time costs, how we can reduce the time spent on the mesh, how we can connect our CAD system with our simulation more efficiently, and how our people can be trained internally in order to perform additional simulations. And of course, automate all those processes in order not to have to do all the work from scratch manually when it comes to rerun a model. So let's check the bigger picture of multi-physics. Today, the products are becoming more and more complicated with interconnected systems which affect the performance of each other and have to be studied and analyzed individually. So in this system, not only systems are interconnected, but also physics, and all the multiple physics phenomena that involved in a system have to be analyzed and studied in order for a complete understanding of the whole picture to be feasible. So let's look some examples to see what we are exactly talking about. First, let's consider this simple piping system where hot gas is inserted from the inlet at the top and runs through the pipes from the outlet at the left and right. There's a flange where it connects the two parts of the piping system, and also a well displaced at the T-junction of the system. And as you can see, in such simplistic model, multiple physics are involved. So when it comes to this, an engineer has to calculate the flow temperature and the flow velocity and use them as input loads on the pipes in order, and based on those loads, the stress and the stresses can be calculated, and fatigue analysis on the piping system can be performed in order to evaluate the life of the piping system. And let's take an even more complicated example, closer to a real engineering use case. Any motor, when it comes to any motor, an electromagnetic transit analysis is required in order to calculate all the forces in each tooth of the stator, which in turn can be used in a frequency response analysis. And based on this FRF analysis, acoustic responses far from the motor itself are calculated. And let's check a real use case, and we are talking about the Nolatos self-injector. And we can see here the multidisciplinary development of the self-injector, which Nolato collaboratively developed with many industries, with many companies, including Altair. The development cycle considers many aspects together, like the co-simulation of the injection process, the misuse in case of bending or opening of the load tray, the manufacturability of the model parts, and the optimization of the ribs. So before we jump into the SimLab, I want to summarize the main challenges while we are trying to tackle multi-physics analysis. First of all, we have to acquire multiple solvers, and we have to find an efficient way to connect them to each other. And of course, automate all these processes. So based upon these challenges, we have a pretty reasonable question if there is a tool that can help us overcome these challenges. And our answer to this is SimLab. So if you wonder what SimLab is a single multidisciplinary development. And this means that it integrates pre-processing, solving, and post-processing in a single graphical user interface and enable us to easily and efficiently set up multiphysics analysis. SimLab was designed upon three main pillars: the multiphysics support, user-friendliness, and automation. And each pillar is meant to help us overcome the previous challenges of multiphysics analysis. So from now on, we will try to explain each one of these pillars. First of all, let's begin with multiphysics support. And when it comes to multiphysics, SimLab supports structural, CFD, thermal, electromagnetics, and as well as coupling of those solutions. And upon that, we have implemented some dedicated tools that help us set up, like say, common use cases in the industry, among the industries, like drop test, PCBs, thermal management, solder fatigue, e-motor acoustics, battery, and so on and so on. Some typical application and simulation times for structural would be linear and non-linear static and dynamics, NVH, impact, durability, structural. For thermal, we have conduction, convection, and radiation. And of course, we can couple those two, structural and thermal. For electromagnetics, as we saw, we have e-motors. For electromagnetics, PCBA reliability and electronic thermal management. And for fluids, we have fluid structural interaction, multi-phase flows optimization, and coupling with discrete element method softwares. And as Panos said, optimization has been a part of our DNA for around 35 years, so it would be unfair not to dedicate 2 slides to show you how you can use our optimization tools through SimLab. At a high level, we may say that in SimLab, we fully support 2 types of optimization: topology and shape optimization. And of course, as Panos indicated before, we have plenty more optimization tools in our portfolio. To begin with topology optimization help us get a good idea about the optimal loading path and eliminate the unnecessary materials at areas that are out of our interest. And this can really reduce our development cycle and get a good performance and a good idea on a starting design. And of course, all of this topology optimization is fully supported in SimLab and can be very easily set it up. And for shape optimization, free shape optimization is a fine-tuning optimization algorithm and help us get the right geometry and the right shape of our component. Here we see the component that was previously developed by topology optimization and how we can get the exact radius of the fillet in the area with the highest stress. Because when we try to optimize our component, we provide to the algorithm our criteria, such as reducing the stress peaks. Moving on to the second pillar of user-friendliness, in order to make it clear, I have to ask you this: if there is a multiphysics solver? And of course, the answer is no. There are many solvers available when it comes to single problem of physics. Like for structural, we can use OptiStruct, Nastran, Abacus, ANSYS. For CFD, we have AlcuSolve, OpenFOAM, NanoFluidX, UltraFluidX, Fluent, StarCCM, and etc. And for electromagnetics, we have FICO, Flux, JMAG, and so on and so on. I mean, there is a jungle of solvers out there. There are millions of solvers, and as you know, it requires a tremendous expertise and experience for us to know all the details and to master those solvers. So we can imagine how difficult it is to gain knowledge of multiple solvers. And this is the gap that SimLab comes to close, because SimLab is a physics-based platform. It uses physics-based toolbars, and this requires I would say zero knowledge about solvers, because we only have to understand the physical phenomenon and set up our analysis using our physics-based toolbars. And all the work and all the details from the solver are handled internally by the SimLab. And last but not least, the third pillar of automation provides several levels of automation. One can use pre-recording scripts in order to rerun a model or set up a model, or use ready templates which help us with the assignment of mesh, material, and property parameters of the model. Of course, using our pre-recorded scripts or our templates enables users with no coding experience to automate their procedure. And of course, Python, for users with coding knowledge, can be fully utilized through SimLab, because it's the main scripting language, and help us automate further based on our needs. So let me take you to this figure to exactly understand how important it is to invest our time to build a consistent and a robust automation tool, because it can help us, as you see, reduce our time spent on multiple applications from weeks to days, or from weeks to hours. So let's see some examples and some user stories in order to better understand the need of multiphysics analysis. In sequential FSI, we first perform a CFD analysis to compute the temperatures and the pressures of the flow, and we can easily use them as boundary condition in the structural analysis in order to apply the thermal and the pressure loads. FSI problems occur when a flow over a structure causes deformation, and this deformation influences the behavior of the flow. So in order to capture this complex phenomena, we have the tool solvers of the flow and the structural solver must be fully coupled by both running in tandem and exchanging data in real time. So for this, AccuSolve, our flow solver, computes the forces and send them to our OptiStruct, and when OptiStruct computes the displacement, send them back to AccuSolve. And this happened multiple times at each time step without the need from the user to intervene. All these are handled by SimLab automatically. Here we have the coupling of flow and district element method to model particle flow, multi-phase flows, and these applications are encountered in many industries like energy, oil and gas, mining, pharmaceuticals, and it's used for resolving inner particle collisions, particle with equipment collisions, to track the particles alone or a set of a particle, and compute the forces in each particle. For electromagnetics, SimLab core solutions offer a complete workflow from parametric sketch to setup solution and post-processing. As you know, in electrical machines, power losses act as heat sources in the thermal analysis. So the iron and the joule losses are computed by our electromagnetic solver, Flux, and provide these losses to AccuSolve as heat sources. And of course, if we want to couple them in a two-way, as before in the direct FSI solution, the AccuSolve again calculates the temperatures and send them back to Flux in order to again compute the power losses. Oops, this should be hidden. I'm sorry. So at last, a little bit of electronics. As Panos mentioned about batteries, we use OptiStract. We use OptiStract in order to calculate the chemical electric reaction and the joule losses on the batteries and the boost parts. And therefore, the thermal management of the batteries can be modeled with AccuSolve, by modeling the cooling effects through convection and FSI. And PCBs, the current that runs through the traces and the components generates the heat, and this heat constantly increasing the temperature of the component junction. And this phenomenon stabilizes when the heat transfer away from the component equals to the power of dissipation of the component. So in this phenomenon, it plays a crucial role in order to effectively track the cooling path of the flow. So, because if we do not have a clear image in the flow path, fatigue like warpage occurs. And lastly, as nowadays everyone is interested in chips with all the fuss about machine learning, a very hot topic is solder fatigue, which is caused mainly from coefficient of thermal expansion mismatch and vibration of the chips. The thermal joint failure. The thermal failure joint is the most common reason why electronics fails. So these tools help us automate all the procedure and evaluate the life of the soldiers. And as you can see, these packages were simulated in SimLab within an hour, and they do not deviate much from experimental live data. And let me share with you some real use cases. This is a belt striper from Bosch. It consists of an e-motor which is moving the two drums, and in a constant loop of the drums, a sandpaper is mounted. And Bosch really achieved a consistency and a cost reduction using SimLab in many physical and manufacturability simulations, like injection molding of the plastic part, where we can see the filling, the packing, and the cooling, resulting to the short fiber orientation. We have a stress analysis, three-point bending, the cooling of the machine, and a drop test of the sander. And another very interesting use case is this of the BMW crankshaft, which helped BMW to reduce the modeling time at 80% and eliminate all the user errors when it comes to manual work. So to summarize everything, I hope it's clear that SimLab is an environment is an environment for multiphysics analysis, but it's not only this. It can help us automate all our procedures and help us model complex components because when SimLab was introduced it was widely known for its capability of tetrameshing and hexameshing. And that's all. And I want to thank you for your time and attention.